thing, but
Is it going to be like a 15 minutes or is it going to be a big one?
I think I'm planning on giving you the whole period. Wow. That doesn't mean it's like a killer.
Just means it has a higher probability.
Open note as usual?
Open note as usual. Yeah, basically all about counting. So, product rules, sum rule, combinations, permutations, Pascal's triangle, maybe pigeonhole stuff. I don't think it'll take the whole period, but I'll give you the whole period if you want. It's hard because we don't do sort of short in-class quizzes every week like I do in some of the other classes. So I don't get a really good feeling for how much time people are spending on things. Well, how much time do you think you spend on that previous homework? With a number of words, with number of numbers with node 5s in them, that kind of stuff. That homework that you just got back.
Oh, no, no.
Yeah, it's like we can go hour and a half.
Okay. Not counting, going to your drawer and pulling out socks repeatedly.
And buying an octopus.
Buying an octopus, training the octopus.
Naming the octopus, putting it in the bag.
Don't name it because then you can't get rid of it.
I know that we did this yesterday, but I'm kind of lost on number 4.
Oh, sure.
Do it one more time. But I think it's...
Oh, is that the octopus socks?
Yeah.
Okay, that's a generalized pigeonhole principle. So generalized principle, n objects, m boxes, at least one box has at least
Did you get this?
ceiling of n over m. So the version we've been talking about is where you have, say, m boxes and m plus 1 objects.
That's right.
Right? And ceiling of m plus 1 over m is 2. Right? It's 1 point something, you round up to a 2. So this would say if you have m plus 1 objects and m boxes, at least one box has at least 2 objects in it. But we can generalize it. If you have 7 boxes, say the days of the week, and you have 25 people, and you imagine putting each person into a box based on the day of the week they were born, right? This is n is 25 objects going into 7 boxes. 25 over 7 is 3.428, and so ceiling is 4. So the generalized pigeonhole principle tells you if you look at 25 people, at least 4 of them were born on the same day of the week. Okay, so on to octopi. So we have 5 colors of socks, and we're going to pick out n socks, and we're going to put them into bins based on their color. And we're going to have at least one bin with at least this many socks. Now we want to find the smallest value of n for which we know at least one bin has at least 8 socks. So find an n so that ceiling of n over 5 equals 8, and find actually the smallest n for which that's true. So if n over 5 is bigger than 7, then its ceiling will be at least 8. Right, so n is bigger than 7 times 5, which is 35. And the smallest n for which that's true is 36. That's the more formal way to do it. You can kind of trial and error and intuit your way there also. And it's basically if you have 36 and you start putting them into bins, 35, best case you can have exactly 5 in each of your, exactly 7 in each of your 5 bins. If you add one more sock, it's got to go into one of those bins. That bin's going to have 8. And then you've got your necessary matches. All right, so I posted a new homework, and we'll talk about this, these concepts today and or Monday. First one, I want you to construct a binary search tree from this data, assuming the data arrives in the order shown. So we talked about how to insert things into a binary search tree. Basically start at the root, and you move either left or right until you get down to a leaf, and then you insert either left or right, depending on how you compare. So all of these letters are different, I hope, and just put them in alphabetical order in a binary search tree. So D is going to be the root, right? And W is going to hang off to the right, and you just keep going from that. And we're going to talk about presently pre-order, post-order, and in-order traversal of trees. We started this yesterday, so that'll help you do D. Yeah.
So in A, when you're constructing the search tree, you would have D and then W would branch off to the right.
Correct.
Would B branch off of W or branch off of D to the left?
How does B compare to D? Is it bigger or less?
Right, okay, so it would go off
So
to the
we'll go
left.
off to the left, yeah.
And then E would go off to the right, but it would go to the left of W.
Correct.
Okay.
Yep. We'll be doing some examples of this. So. And then tell me what the level of each node is. So remember, level was the number of links from the root to a node. So the root has a level of 0, and all the others have a level bigger than 0. And then what's the height of the tree? That's just the largest level of any node. And then concoct a balanced binary search tree. In other words, one that satisfies that balanced definition. And don't go to Wikipedia and find out how to balance trees and try to apply that, because that's a horrible nightmare. Just think about how you could write a balanced binary tree from this data. Don't worry about the order in which it comes in. Just try to come up with a tree. But do it by playing around with it. Don't just look up an algorithm, right? Because the values from messing with it and looking at how things lay out. Question 2, we're going to talk about recursion trees today or Monday. And I want you to draw a recursion tree showing how we calculate the 8th Fibonacci number. So we have a recursive algorithm for Fibonacci numbers. It says Fn equals Fn minus 1 plus Fn minus 2. And the first and second Fibonacci's, I'm telling you, are both 1, and those are our base cases. So if you want to find Fibonacci 1 or 2, you just use these facts. If you want to find Fibonacci 3 or higher, you use this. And to use this, you need to recursively find these other Fibonacci numbers. And we're going to talk about how we can use a tree, not a binary tree anymore, but a tree to organize the way that recursive calls play out. So I want you to do that for the 8th Fibonacci number. Big sheet of paper. Okay, try to work neatly. You'll probably want to do this on scratch paper and then redraw it. But it's kind of cool once you get there. Question 3, with misspelled binary in it. So here's the search algorithm that I first put on the board yesterday. It's not an efficient search algorithm. Okay, as I think Yosha pointed out, it's more efficient to say if the data is less than the root, then do this, otherwise do this. Suppose we have an algorithm that does both of those, though. And then if either of those found our data, we return true, otherwise we return false. I want you to think about how much time this algorithm will take. I'm not looking for a number, I'm not looking for a formula, I'm looking for a discussion. Okay, some speculation about what this algorithm will do on a given tree. So think about it. Okay, this is a very open-ended question. There's not really a right or wrong answer. I just want you to explore this and then write up a few sentences, a paragraph, whatever you think, discussing how long this will take for a tree with, say, n nodes, where n could be really small, could be really big. This is kind of easing us into our week 10 topic, which is going to be complexity of algorithms and efficiency of algorithms. So I graded your programming assignment over the weekend and posted those, but we didn't really talk about them. So I'll say nice job on the programming assignment. I think most or all people had a good solution for that. There were two kind of fundamentally different ways to go about putting Pascal's triangle. One is to use the fact that that you can find the elements using formula for combinations. So n factorial over r factorial n minus r factorial. And that's challenging when you start getting into the deeper rows of Pascal's triangle, because factorials grow so quickly. So you end up using longs or longs or BC or something like that. Remember, does BC do factorials? But the other way is to use this property that each entry, other than the ones on the end, is the sum of the two entries above it. So 4, 6, 4, yeah.
Okay, well, we have like integers, floats, long doubles, stuff like that. But if even the longest one of those wasn't enough to hold a number, does C go low enough that we could make our own way of representing it, or would we have to use assembly?
You can define your own data type. You could say I'm going to store my number in an integer array, and each element's going to hold one digit. And you could make your arrays 1,000,000 integers long, and now you can work with 1,000,000 digit numbers.
Okay.
And BC basically does that, right? So we can do ridiculously long number times another ridiculously long number, and it'll just tell us what the answer is. And it's doing that by basically doing pencil and paper multiplication, or something equivalent to that.
Interesting.
All right, so if you just store your digits in an array, you can multiply this by this. If you get 81, right, your product digit is 1, and you have to carry an 8 over to the next place, and so on. But you and I can do it. We can definitely teach a computer to do it. And I think there's some libraries that you can use from C that support that. So you don't have to go out to BC. But the easier way for this particular problem is just to add the numbers in the previous row to get the next row. And they don't grow very bigly. The things that you use to compute them like this grow horrendously fast, but the actual values don't grow very quickly at all. By row 15, we're somewhere in the thousands for the biggest numbers in the middle. And it's not a bad algorithm, so this was my version of it. And this would only work up to 100 rows, but I just had an array for my current row. I had another array as a temporary, and then my row column and the obligatory integer I. So I initialized row 0 and 1 to 1. That gave me my second row. And then I basically said copy my current row to my temporary, and then for everything except the endpoints, set my new row's element C to a sum of the elements above it. So I just read those out of my temporary copy, added them together, and then I set the last one over here. And since I started from 1, I never changed row 0, which is just my leading one. And then I printed it out, and I just did that in a loop up to row 16 in this case.
So let's say we just need the hundreds row. Can we just calculate that one, or we need to be dependent on the...
With this approach, you'd have to go through all 99 rows before it. It's still less work, though, than just calculating 100 factorial, even if your system can do that. So copy is just a straightforward copy from your input array to your output. And then print, I got fancy with it, so I spaced over based on the row number that you were in and forced my output to be 4 characters. So it gives you somewhat pretty output. There we go.
It's beautiful.
Yay. The things I do to entertain myself at home. All right. So your third programming assignment is going to be related to graphs. And we haven't started talking about graphs yet. So we may get to graphs today. If not, we'll get to it Monday. And I'll post your assignment and give you like a week after it's posted. All right, so we were talking about trees. Tree, just to play with. I'll probably erase it without doing anything. But it's a binary search tree. So if I did this correctly, everything to the left of a node is smaller than the node. Everything to the right of the node is bigger than the node. And what did we end our discussion with yesterday? Searching?
Traversal.
Traversal.
Okay, good.
With the LNR.
Good, thanks. Did you have a question? Okay. So LNR traversal was saying traverse the left subtree, then visit the node, then traverse the right subtree. And we wrote, I think, a recursive algorithm for doing that. Did we?
Yes.
Okay.
Wait, yeah, we did. That was the pseudocode.
I'm going to work with it anyway. So how do we traverse a tree?
At least you called it search. We didn't write traversing.
No, we didn't.
We would traverse it with the search.
Okay, we'll traverse it here anyway. It's very similar to the search function. If the tree is null, we just return. There's nothing to visit. Otherwise, we say traverse the left child, and then print the root, and then traverse the right child. Here's our whole algorithm, and it actually works. And for a binary search tree, this left node right, which is also called in order, will print out our nodes in started order, increasing order in this case. What if we visit the right and then the root and then the left? Descending order. Not too startling. but what if I do this? I print the root node, and then I traverse the left, and then I traverse the right. Do I get the same output?
No.
Clearly not, because the first thing it prints is going to be different. It's going to bounce around. So this is called node left, right. Visit the node first, and then traverse the left subtree, and then traverse the right subtree. That's called pre-order. And it would probably give us something like this. It would give us a 12. And then we traverse this subtree, which says print out the root, and then traverse the left subtree, which says print out the root, traverse the left, and then traverse the right. That completes the 12, it completes the left subtree. Now we traverse this, which will give us a 20, and then 18, and then traverse this. I should have made my tree simpler. 30, and then traverse this, which will be 25, 23, 26, and then traverse the right, which will visit the node, and then the left. And we'll put a small question mark just in case I made typos. Yeah.
Once you reach the bottom of a tree, how do you know what node to go back up to?
Got to remember.
But how do you tell the computer?
It's got to remember. Now, when you do this recursively, when I say traverse the left and it comes back into traverse, after I eventually return, it's going to come back here, and all my variables are going to be exactly what they were. Right? When you make a recursive call, it saves all your local variables. It's got their own copy of them, and it kind of starts from scratch. When you eventually return from that call, whether you went down one more level or 100 more levels, when you return, you're back where you were. So if I had my thumb right here to remember that this was my node, when I come back from my call, my thumb's still sitting here. And it's fairly magical.
It's kind of just like the fourth thing we just talked about,
Yeah.
where you're popping up right where you were, and so that's what the clone does.
Yeah, yeah.
It's kind of like creating its own stack.
Mm-hmm.
Right?
Yeah, and it uses the stack to make recursion work. So the in-order traversal should end up being 2, 4, 6, 12, 18, 20, and cheating. All right, and finally there's left-right node, which is called post-order. We go all the way to the left, we go all the way to the right, and we visit the node last. So left, left, left can't go any more to the left, can't go any more to the right than 4, and then visit the node, and then 6, and then traverse the right tree post order. So 18, traverse the 30, which is traverse the 25, 23, 26, 25, 37, 40, 30, 20, 12, another question mark. I missed something. And we can code post-order traversal just by putting our print statement down there. Does this work? Of course. It works because we believe it. Right? If we believe that this will successfully traverse a tree of height 2, then this is guaranteed to successfully traverse a tree of height 3. Because it's going to traverse the left subtree, which has a height of 2 or less, and then it's going to print the root, and then it's going to traverse the right subtree, which has a height of 2 or less. So if we believe this works for a height of 2 or less, then that algorithm will work for a height of 3 or less.
So it's kind of like commutative, where it'll always work, it's just going to be a different output.
Yeah.
Okay.
So it's an inductive thing, right? As long as we have a base case, and we know that if it works for a height n, it will work for height n plus 1, then we know it works for any height n. So what's our base case here? Null. If the tree is empty, it won't print anything. That's a successful traversal of a null tree.
That doesn't sound meaningful.
It doesn't. But if it has a single node, then it will successfully traverse the left subtree, which is empty. It will print out the root node, and it will print nothing when it traverses the empty right subtree. That's a successful traversal of a single node, a tree with a height of 0. And you can go to whatever level you feel comfortable extending it beyond. So yeah, it's really just kind of an inductive verification. And this requires strong induction. I think I glanced over strong induction. Our usual induction says, assume a base case like P of 0, and then show that if P of n is true, P of n plus 1 is true. Strong induction says, assume a base case P of 0, and then show that if P0 through Pn is true, P of n plus 1 is true. But we have to assume that all the propositions less than or equal to n are also true. So we make this much stronger assumption. But it's equally valid, because if 0 is true, then we know 1 is true. And if 1 is true and we know 0 is true, the fact that 1 implies 2 means that if 0 and 1 are true, then we definitely have shown 2. And if 2 implies 3, then knowing 0, 1, and 2 definitely implies 3. But you can build yourself up, right? You start from 0, you show 1, now you know 0 and 1 are true. You show 2, now you know 0, 1, 2 are true, and you can show 3, and so on. And this is a case where if our tree has height n, the left subtree may not have height n minus 1. But we know it'll have a height less than n. So that's where we're using the strong induction. What else can we do with this? That's probably enough recursion for now. All right. In-order traversal on a binary search tree gives us our data in sorted order. Why would we want to do some other traversal? Let me give you an example. And so we're going to start talking about other things we can do with trees. And again, they're not necessarily binary trees. But here's one thing we can do with a tree. We can represent arithmetic expressions. So for example, this is a representation of the expression 5 times 7. This is a number 5, this is a number 7, this is an operator that takes 2 operands. The 2 operands are 5 and 7. This is 35. This 7 could be another operator. Could be 2 times 3.
That's 6.
That's 6. I know, it's not 7. I picked a prime.
You and your primes.
Me and my primes. So this is 5 times the quantity 2 times 3. And maybe instead of having a number over here for 5, I might have, I don't know, 6 plus 3. And so this is 6 plus 3 times 2 times 3. And if I had different parentheses, if I wanted 6 plus 3 times 2 times 3, it's not too bad. Here's a plus. Here's 6 on the one side. And on the other side, I have a product. I have 3 on one side, and on the other side, I have a product of 2 and 3. So pretty much any expression we can write like this, we can represent with a tree.
How would you store an operator? Or it's just in the code.
Pick a symbol for it, pick a number for it. So in C, we could define a structure that has a flag saying whether it's an operand or an operator. If it's an operand, then the other part of the structure is just a number. If it's an operator, then the other part of the structure is a number that represents plus, minus, times, divide, something like that. Or you just store a pair of things. Or just store it as a character. Or a string of characters. All right. So let's look at a particular expression. So what expression does this correspond to?
2 plus 5 plus 5.
Okay. With the parentheses like that, right? Because we've got to evaluate this thing, and then evaluate this thing, and then multiply them together. Evaluating expressions with parentheses is kind of funky. It takes remembering where the parentheses start and when you find a closing parenthesis, gobbling up everything up to the matching open parenthesis, and then continuing from there. And it's kind of a funky process. But there's a different way to evaluate this expression. And it turns out all we have to do is a post-order traversal. So if we traverse this tree post-order, we go all the way to the left. Left, go left, we come down here, there's a 2. And so we're traversing this whole tree. First we traverse the left subtree, that's this piece. So to traverse that, first we go to the left. And when we traverse this tree with just a root, we're going to get a 2. Then we're going to go to the right. And then we're going to visit the root. That's the L on the whole tree. Next we have to do the R on the whole tree. So traverse this thing, left, right, node. Traverse to the left, that gives us a 4. Traverse to the right, that gives us a 5. Visit the root, that gives us a plus. That's the R part of the original tree. Now we do the N part, which is just the root. That's a star.
That syntax doesn't make sense.
That's like Hewlett-Packard for these calculators.
That is like Hewlett-Packard calculators. This is called postfix notation. So old HP calculators, you typed in your operands first and then your operation. So if you want to do 2 plus 3, you would type 2 and then 3 and then plus. And this corresponds to this in what's called reverse Polish notation or postfix. Take 2, take 3, add them together, that gives you 6. Take 4 and 5, add those together, that gives you 20. take the 6 and the 20, multiply them together, and you get,
6 and 5.
yes.
Yeah, where did 20 come from?
Sorry, 2 plus 3 is 5, 4 plus 5 is 9. Multiply those, and you get 45.
So this kind of lets you read it left to right?
It lets you read it left to right.
Did you say
You never need parentheses.
Did you say reverse Polish?
Reverse Polish, yeah, RPN.
Okay.
I've actually got a program on my calculator that functions this way. I didn't realize it before, but it's supposed to be for doing arbitrary large arithmetic, which is fine. But what it does is it has you input the numbers, all the numbers you're going to work with, and then you press addition or multiplication or modulo or whatever it is, and it takes the bottom two in the line and does the operation and puts them in the bottom line, shifts everything down.
Nice.
I didn't really realize it was doing this operation, but that's what it
Yeah.
probably is doing.
Yep. And that's exactly how you evaluate a string like this. So you begin here, and if you find a number, you push it on a stack. Do you know about stacks? Raise your hand if you know about stacks. Do you love stacks? Raise 2 hands. You take your numbers and you put it on your stack, right? If you don't know stacks, you just write it down here. You take your next number and you put that on the top of the stack. When you come to an operator, you do the following. Take the 2 things off the top of the stack, operate, put the answer on the top of the stack. So we get rid of this, we get rid of this, 2 plus 3 is 5, and we put a 5 on the top of the stack. We find a 4, that goes on the new top of the stack. We find another 5, that goes on the top of the stack. We find an operator, take off the 2 things on top, apply the operation, 5 plus 4 is 9, and put that on the stack. Now we've got another operator, take the top 2 things off the stack, that's the 9 and the 5 is 45, apply the operation, put the answer on the stack. When you're done, your stack should have 1 thing on it, that's your answer. So in 222, we'll make a program to do that, to play around with stacks. It's really easy to do if you do it this way. There's almost no housekeeping to worry about. So post-order traversals, good for evaluating arithmetic expressions. That's a good enough reason to know it right there.
It's really cool.
What about and
I don't know what we use pre-order for. It's probably a good one.
So, is this how an algebra solver would do it, a computer algebra solver?
Yeah, and this is how compilers work too. When you have an expression in C like this, right, it'll generate code that probably does something like that, depending on the compiler.
Well, I was thinking maybe it would store it into the tree structure, so it could run it that way, maybe?
Yeah, there's systems that do that.
Wouldn't a pre-order just allow you to read right to left if you do arithmetic?
Possibly, yeah, that might be.
I mean, it almost certainly would be, wouldn't it?
Well, so let's see what node left right does. So star plus 2, 3 plus 4, 5. Yeah, that seems to be. Although we're kind of doing things in a different order too.
Yeah, I guess if you had division in there somewhere, you could
Yeah, or
put
subtraction.
Or subtraction, yeah.
Yeah,
Huh,
that's cool.
weird.
What else can we do with trees? See what? Plant them. Make forests.
I almost went further than I decided it was too obvious.
You say you have a red black tree that can mean a lot of different things to a lot of people.
Yeah, right.
is this the way that views work on, not exact, but somehow view work in SQL Server? Just we have loops over there.
Possibly. I don't know definitively which systems use this.
Okay.
I can imagine compilers and interpreters doing this kind of procedure for evaluating expressions, but I don't know if a modern C compiler does that, for example, or if a database server does that. But these kinds of ideas of being able to descend down a branch and then come back to where you were and descend in a different way, those permeate everything. And there's certainly a lot of that going on in databases. So web browsing, right? So you go to yahoo.com, because I stumble onto that every now and then. I do fantasy football, so when I exit, I'm always at yahoo.com. And so you start reading, and oh, let's go down to the sports section, and let's go down to the hockey section, and let's go down to a section about Wayne Gretzky. And we read that story, and we're done with it. And we go back one page to the hockey section, and now we come down to scores. And we read our scores, and we go back to the hockey section, we go back to the sports page, and now we come down to basketball. And we come down to tickets, and we come back up, and eventually we get back to yahoo.com, and we follow the obligatory UFO link to sightings of UFOs, and so on, right? And you can use a tree to organize your traversal of this website. And as we pointed out before, there might be links in there, so it might not strictly be a tree. But the idea is, you're using your thumb to remember, okay, I was looking at the sports page, and you might descend really far down. But eventually, if you hit the back button enough, you come back to here, and at this point you could descend down another branch, or you could pop up another layer. And you can map all of that with a tree. Pretty easy to do.
And this makes sense because once you go back to sports and you got into basketball, you can't forward back to hockey.
Right,
Yeah.
right.
Well, I mean, even with links thrown in, if you look at how links actually function, and you don't look at this as you browsing a website, but as your browser getting information or the web server handling it,
Yeah.
all the link's doing is saying, okay, we're starting at yahoo.com, go to sports, go to hockey, go to Gretzky. You came from basketball and tickets, but that doesn't matter.
Right.
That's how we're going to get that information that you want. So it still works.
Right. And this is how a spider works.
Yeah.
Right? When you make a spider that crawls a web page or crawls the web, right, it starts somewhere and it just moves down the page and follows every link. And when it gets to a link, it pulls up that page and it follows every link. And it has to detect cycles so it doesn't get stuck in a loop. But other than that, it's just a big recursive visit every link on this page. And you can write it with a really simple recursive algorithm. Right? If this is a link, then crawl from this point down. And your crawl routine basically says if there's nothing on this page, I'm done. Otherwise, print out the link and go down, and every time you find a link, crawl it. I don't know if crawl is a technical term.
And that's you've heard of the dark web. That's what this is. It's things that aren't referencing the structure that you can't directly get to by going to those aforementioned links.
Yeah.
That's all it is.
So a disconnected graph. All right, wow, we're out of time already. So we still have to talk about decision trees and 20 questions and depth first versus breadth first. And then we will...
Did we talk about recursion trees?
No, and then we'll talk about recursion trees. So I'll give you a week after we get to that to do the homework. So we'll have time.
Do you want a quiz tomorrow?
Your problem one? Yes, there's a quiz tomorrow.
1 to 15.
There's 2:15, yes. And 2:24. Yeah.
Had a particularly boring weekend coming up?
Yeah, right.
What material?
2:15 is counting.